Hello everyone. For today's lesson, let me first of all show you some properties about definite integral. First property, integral from a to b, f of x plus g of x dx equal to the integral from a to b, f of x dx plus integral from a to b, g of x dx, which says if there are two functions inside integral, I can separate it into two integrals with the same limit, with the same upper and lower limit. How does that make sense to you? Let's look at the definition of definite integral. Definition of definite integral says integral from a to b, f of x dx is the limit as maximum delta Si approach to 0, sigma I from 1 to n, f of Si star times delta Si. That's the definition of definite integral. If we have integral from a to b, f of x plus g of x dx, what do we get? So instead of function f of Si here, I plug in f and g for f. That's the limit as the maximum delta Si approach to 0. Sigma I from 1 to n, f of Si star plus g of Si star times delta Si. So for integral of f of x plus g of x, I plug in f and g for function f here. Then if I simplify, limit stays the same. I can distribute delta Si. I can distribute delta Si into the sigma. Here I get f of Si star times delta Si plus g of Si star times delta Si. I first of all distribute delta Si into the parentheses. Next, I can separate the sigma notation into two sigmas. If there are two terms inside a sigma notation, I can separate it into two sigmas. Limit stays the same. Sigma I from 1 to n, f of Si star times delta Si plus another sigma I from 1 to n, g of Si star times delta Si. Then, if there are two terms inside a limit, I can separate this limit into two limits. So I got limit maximum delta Si approach to 0 of sigma I from 1 to n, f of Si star times delta Si plus another limit maximum delta Si star goes to 0, sigma I from 1 to n, g of Si star times delta Si. Then, by definition of definite integral, this limit equal to the integral from a to b, f of x dx. This limit, if you compare this limit with this limit, everything looks exactly the same. The only difference is function f and g. So that's integral from a to b, g of x dx. That's how we get the formula. Integral from a to b, f of x plus g of x equal to the integral of f of x plus integral of g of x. That's the first property. Second property says integral from a to b, k times f of x dx. K times f of x dx equal to integral equal to k times integral from a to b f of x dx, which says if we have a constant times a function inside integral, I can always pull out the constant, take the integral of the function first, and then multiply the answer to the constant. How does that make sense? Same thing, we can look at the definition of definite integral here. If we have integral from a to b, k times f of x dx, what do we get? If we plug in kf for function f, we have limit maximum delta si approach to 0, sigma I from 1 to n, k times f of xi star. Here I plug in kf for function f here, times delta si. Since k is a constant multiple inside sigma, I can always pull out a constant. Limit stays the same. Since k is a constant multiple inside sigma, I can pull out k. Get k times sigma I from 1 to n of f of si star times delta si. Then when we have a limit of constant times a function, I can always pull out constant inside the limit. I can always pull constant outside the limit. I get k times limit maximum of delta si approach to 0, sigma I from 1 to n f of si star times delta si. And this is integral from a to b f of x dx. This looks exactly the same as this limit here. Let's integral from a to b f of x dx. So I get k times integral from a to b f of x dx. That's why when we have a constant times a function inside integral, I can always pull out the constant. Next, integral from a to b f of x dx. If we integrate from left to right, usually we consider the function the integral is positive. If we integrate backward, if we take integral from b to a, we consider this integral is negative. If we integrate from left to right, for area under the curve, if we integrate from left to right, we consider this is positive area. If we go backward, we consider this area is negative. That's why integral from a to b f of x dx is negative integral from b to a f of x dx. If we go from left to right, we consider an area is positive. Now if we go backward, we consider an area is negative. Next, integral from a to b f of x dx plus integral from b to c f of x dx. Integral from a to b f of x dx plus integral from b to c f of x dx. What do we get? Let me show you a picture. It will make more sense to you. Consider that's the graph y equal to f of x. Integral from a to b f of x dx represent this area. Integral from a to b f of x dx represent this area here. Suppose c is here. Now integral from b to c f of x dx represent this area here. Area under the curve from b to c. That's area under the curve from a to b. And that's area under the curve from b to c. If we add them up, what do we get? If we add them up, we have area under the curve from A to C. If we add them up, we totally have area under the curve from A to C. That's why here, integral from A to B f of x dx plus integral from B to C f of x dx equal to integral from A to C f of x dx. Next property. If f of x is greater or equal to 0 for all x in the interval AB, if f of x is greater or equal to 0 for all x in the closed interval AB, then the integral from A to B f of x is always greater or equal to 0. This says if f of x is positive, is greater or equal to 0 on the interval from A to B, then the area under the curve from A to B is positive. That's what this property says. If f is positive, then the area under the curve from A to B is positive. And similarly, if f of x is less than 0, is less or equal to 0 for all x in the closed interval AB, then the integral from A to B f of x is less or equal to 0. Think of this. If function f is negative, then the area under the curve from A to B, then area under the curve from A to B, this area is actually above the curve. So the opposite of above is under. So this area is actually negative. If function f is negative, then the area from the curve to x-axis is negative area. So if f of x is less than 0 on the interval from A to B, then the integral from A to B f of x is negative, is less than 0. Next property. If f of x is between little m and big M, for all x in the interval AB, then the integral from A to B f of x dx is between little m times b minus a and big M times b minus a. So here, if f is between little m and big M, this little m here is called a minimum. This big M is called a maximum. If f of x is between two constants, little m and big M, for all x in the interval AB, then the integral from A to B f of x dx is between m times b minus a and big M times b minus a. How does that make sense? Think of this. That's function f, y equal to f of x. That's the graph of function f. F of x is greater or equal to little m. F of x is above little m, and it's below big M. On the interval from A to B. little m is the minimum, big M is the maximum of function f. Then integral from a to b f of x dx, it represents the area under the curve from a to b. What does this represent? What does m times b minus a represent? Little m is here. That's the height of this rectangle. Little m is here. That's the height of this small rectangle. B minus a, larger number minus smaller number, that's the width of this rectangle. B minus a, that's the width of this side. Width times the height is the area of this rectangle. Width times this height is the area of this rectangle. Here you can see that the area under the curve is more than the area of this rectangle. That's why integral from a to b f of x dx is larger than m times b minus a. Then what's big M times b minus a? Big M is the height of this edge. Big M is the height of this edge. And we know b minus a is the width of this edge. Width times height is the area of this big rectangle. Width times height is the area of this big rectangle. We know that since f is below m, area under the curve is less than the area of this big rectangle. So area under the curve is less than the area of this big rectangle. That's why we have integral from a to b f of x dx is between m times b minus a and big M times b minus a. Next property, it says if function f is greater than or equal to function g for all x in a closed interval from a to b, then the integral from a to b f of x dx is greater than or equal to integral from a to b g of x dx. How does that make sense? Let me show you a picture first. Suppose function f is greater than function g on the interval from a to b. If function f is greater than function g, means function f is above function g. Then integral from a to b g of x dx represent area under the curve from a to b. That's integral from a to b g of x dx. It represents area under the curve g of x from a to b. What does this mean? Integral from a to b f of x dx. Integral from a to b f of x dx g of x f of x dx, it represents area under the curve f of x from a to b. Integral from a to b f of x dx represents area under the curve f of x from a to b. We can clearly see that since f is above g, area under f is more than area under g. That's why if f of x is greater than g of x, then the area under function f is more than area under g. Those are the properties of definite integrals. Next, let me introduce the evaluation theorem. First of all, let me introduce what it is. Let f be a continuous function. On the interval from a to b. Then, by the definition of definite integral. By the definition of definite integral, integral from a to b f of x dx equal to the limit as the maximum delta Si approach to 0, sigma I from 1 to n f of Si star times delta Si. That's the definition of definite integral, which means if function f is continuous on the interval from a to b, we first of all divide interval ab into n subintervals, s1, s2, x3, xi minus 1, si, the second last one is xm minus 1, and b is sn, a is x0. I divide the interval ab into n subintervals. The intervals may have different widths. This width is smaller, this width is larger, this is smaller, this is larger, and so on. Then on each subinterval, we pick sample point. On each subinterval, pick sample point, called S1 star. And then use the sample point to approximate the height. Then find the area of the rectangle. So in the ith interval, the sample point is xi star. And so on. In the last interval, the sample point is xn star. Then use the sample point to approximate the height of a rectangle. And then for area of each rectangle, take width times height. The width here, for the first width, delta S1, we use S1 minus X0. For the second width here, delta S2, we use X2 minus S1. And in general, in the I subinterval, delta Si, we use Xi minus Xi minus 1. In the last subinterval, delta Sn, we use Sn minus Xm minus 1. Then use the width times the height. We find the area of each rectangle. And then adding up. Sum is adding up. We find approximate area under the curve. And then we take limit as the maximum delta Si approach to 0. That's the actual area under the curve. Next, let me introduce the antiderivative of f. Let big F be an antiderivative of small f. Let big F be an antiderivative of f. Then the small f is the derivative of big F. Since small f is the derivative of big F, and it's continuous, and small f is continuous on the interval from A to B, then big F is differentiable on the closed interval AB. Since small f is the derivative of big F, and it's continuous on the interval AB, if the derivative of big F exists and it's continuous, then we say big F is differentiable on the closed interval AB. Hence, big F is continuous. If a function is differentiable, then it must be continuous. Hence, big F is continuous on the closed interval AB. Now, if we divide the interval AB into n subintervals, if we divide interval AB into n subintervals, it looks like this. That's interval AB. I divide interval AB into n subintervals. That's the first one. That's the second one. Side interval is narrower, side interval is wider. That's the first interval, second interval, third subinterval. That's xi minus 1, that's xi. That's the I subinterval. And continue. That's xn minus 1, b is sn. That's the last subinterval. Here a is x0. That's the first subinterval, second subinterval, third subinterval. And continue, that's the I subinterval. And that's the last, that's the n subinterval. So if we divide interval AB into n subintervals, call interval from x0 to s1, interval from x1 to s2, x2 to x3, and the last one is interval from xn minus 1 to sn. Then since f is continuous and differentiable on the interval AB, on the entire interval AB, since big F is continuous and differentiable on the entire interval AB, then big F is continuous and differentiable on each subintervals. Then big F is continuous and differentiable on each subintervals. Then you can say big F is continuous and differentiable on the interval xi minus 1 to si, where I is 1, 2, 3 up to n, which means big F is continuous and differentiable on each subintervals. When I is 1, it's the first interval. When I is 2, it represents the second interval. When I is 3, it's the third interval. When I is n, it represents the last interval. Then here, big F is continuous and differentiable on each subintervals. Next we call the mean value theorem. That's what you learned last semester. Mean value theorem. What's mean value theorem? That's what you learned last semester. Mean value theorem says if function f is continuous on the open interval, on the closed interval AB. If f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a real number C belongs to the closed interval AB, belongs to the open interval AB, such that f prime of C equal to f of B minus f of A over B minus A. That's mean value theorem. And this expression f prime of C equal to f of B minus f of A over B minus A, this formula is equivalent to B minus A times f prime of C equal to f of B minus f of A. That's mean value theorem. It says if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a real number C belong to the open interval AB such that f prime of C equal to f of B minus f of A over B minus A. This formula is equivalent to the formula B minus A times f prime of C equal to f of B minus f of A. This is mean value theorem. That's what we learned last semester. Today we will use it here. Since big F is continuous and differentiable on each subintervals, since big F is continuous on the closed interval xi minus 1 to si and differentiable on the open interval from xi minus 1 to si. Since f is differentiable on the closed interval, then it must be differentiable on the open interval, because open interval is the subset of the closed interval. So since f is continuous on the closed interval and differentiable on the open interval for all I equal to 1, 2, 3 up to n, then by the mean value theorem, on each subinterval from si minus 1 to si, there exists a real number C So on each subinterval from x0 to s1, there exists a real number c. On the second interval from s1 to s2, there exists another real number c. Those are different real numbers. So let me call this c1, c2, c3. In the ith interval, let's call it c sub I. In the nth interval, let's call it c sub n. So on each subinterval, there exists a real number c sub I belong to the subinterval. Such that mean value theorem says b minus a times f prime of c equal to f of b minus f of a. On the interval ab, we have b minus a times f prime of c equal to f of b minus f of a. If we apply the formula here, what do we get? Here the interval is from si minus 1 to si. So si minus 1 represents a, xi represents b. So if we apply the formula here, we have f of si minus 1. Here we have b is si. A is si minus 1. That's a, that's b. So b minus a is si minus 1 times f prime of c. Here the function is big F, so the f prime of c. In the ith interval, we have a constant c sub I equal to f of b minus f of a. Here b is xi. We write big F of si, f of b minus f of a is xi minus 1. So by mean value theorem, xi minus si minus 1 on the ith subinterval, si minus si sub xi minus 1 times f prime of ci equal to f of si minus f of si minus 1 by mean value theorem. Next, let's try to rewrite this expression. What's xi minus si minus 1? What's si minus si minus 1? We know that in general, si minus si minus 1 is the width of the subinterval, delta si. In general, delta si is si minus 1. So si minus si minus 1 is delta si. Since si minus si minus 1 equal to delta si, what's big F prime? What's big F prime? We know that big F is the antiderivative of small f. Then we know that small f is the derivative of f, of big F, which means small f is big F prime. Since si minus si minus 1 is delta si, and big F prime is small f, then the above expression can be written as delta si times small f of ci. That's delta si, that's small f of ci. In general, for multiplication, I can always switch order. A times b is always the same as b times a. So I can switch order. I can write f of ci times delta of xi. I write f of ci first times delta of si equal to big F of si minus big F of si minus 1. So this expression can be rewritten in this form. Now let's look at the definition of definite integral. Next, let's look at the definition of definite integral. Integral from a to b f of x dx. By definition of definite integral, that's the limit as the maximum Si, maximum delta Si approach to 0, sigma I from 1 to n, f of xi star times delta Si. What's Si star? Si star is the sample point on each subinterval. It could be any point on the subinterval. So since sample point could be any point on the subinterval, I can choose my Ci, C1, C2, C3 as the sample points. So by letting Si star equal to Ci, by letting Si star equal to Ci, this expression can be rewrite as limit stays the same, sigma stays the same, Si star is the same as Ci, since I choose Ci to be the sample point. Si star is Ci, since I choose Ci as the sample point, times delta Si. And by mean value theorem, f of Ci times delta Si is big F of Si minus big F of Si minus 1. Limit stays the same. By this expression here, by the mean value theorem, f of Ci times delta Si is big F of Si minus big F of Si minus 1. Now, next, expand the sigma notation. Next, I'll expand the sigma notation. If I expand the sigma notation, what do I get? If I plug in 1 for I get f of S1. 1 minus 1 is 0, minus f of x0. If I plug in 2 for I get f of S2. Minus, here, 2 minus 1 is 1, minus f of S1. If I plug in 3, I get f of x3 minus f of x2, and so on, until the last one. For the last subinterval, I plug in n for I get f of Sn minus f of m minus 1. Now let's observe this expression here. In the first term in the first bracket we have f of xi. In the second bracket we have negative f of si. So these two expressions can cancel. Now, in the second bracket we have f of s2. In the third bracket we have negative f of s2. So these two expressions can cancel. So eventually we have one term left in the form. Eventually we have one term left in the form. If there's a one term left in the form, it must be one term left at the end. Eventually we have negative f of s0 plus f of sn. Eventually what's left is limit as maximum delta si approach to 0. What's left is f of sn minus f of s0. What's f of sn? What's sn? What's s0? Sn is always b. x0 is always a. So limit stays the same. We have limit delta si approach to 0, f of b minus f of a. Since both a and b are constants, limit of constant is the constant itself. Since both a and b are constants, limit of a constant is the constant itself. So this expression equal to f of b minus f of a. So integral from a to b f of x dx is f of b minus f of a, where big F is the antiderivative of small f. And the expression here, integral from a to b f of x dx equal to big F of b minus big F of a, is called the evaluation theorem. Next, let me give you the formal statement for the evaluation theorem. Evaluation theorem says suppose f is continuous on the closed interval ab, then the definite integral from a to b f of x dx equal to big F of b minus big F of a, where big F is the antiderivative of small f. Evaluation theorem says definite integral from a to b f of x dx is big F of upper limit minus big F of the lower limit, where big F is the antiderivative of small f. Now, based on the evaluation theorem and the expression about antiderivatives, let me show you some notation for integrals. Those are the general notation for integrals. Integral from a to b f of x dx. This is called the definite integral. And by evaluation theorem, we know that definite integral from a to b f of x dx equal to big F of an upper limit minus big F of the lower limit. That's how we evaluate definite integral. The integral without limits, f of x dx, that's called the indefinite integral. That's called the indefinite integral. Indefinite integral f of x dx equal to big F of x plus c, where in both expressions, big F is the antiderivative of small f. That's how we evaluate definite integral and indefinite integral. Next, let me show you some examples. Evaluate each of the following integrals. First example, integral from 1 to 4, x to the power 4 minus 2x minus 3 dx. According to evaluation theorem, we first of all take antiderivative. We take antiderivative for each term individually. So for first term, we get x to the power 5 over 5. For the second term, we get 2x squared over 2. For the last term, for number 3, the antiderivative is 3 times the variable, which is x. That's constant rule. Antiderivative of a constant is the constant times the variable. Then we evaluate from 1 to 4, which means I plug in 4 and then plug in 1 and take difference. If I plug in 4, 4 to the power of 5 is 1024 over 5. If I plug in 4 here, 4 squared is 16. 16 times 2 divided by 2 is 16. If I plug in 4 here, 3 times 4 is 12. If I plug in 1, I get 1/5. 1 squared is 1. 1 times 2 divided by 2 is 1. If I plug in 1 here, 3 times 1 is 3. Then, evaluate this. Here I use my calculator. I get 903 over 5. That's the answer to this definite integral. Next, integral from 4 to 9, square root of x dx. So first step, take antiderivative. Square root of x can be rewritten as x raised to a half. Take antiderivative is power rule. Add 1 to the exponent, I get 3 over 2. And then divide by the new exponent. Divide by 3 over 2. Evaluate from 4 to 9. Then we'll have a function divided by a fraction. It's the same as saying we multiply by the reciprocal. So we get 2 over 3 times x raised to 3 over 2. Evaluate from 4 to 9. If I plug in 9, 9 to the 3 over 2 is 27. If I plug in 4, 4 raised to 3 over 2, 4 raised to 3 over 2 is 8. That's 54 over 3 minus 16 over 3. 54 take away 16 is 38. So the answer is 38 over 3. Next example, integral from -2 to 6, 2x minus 1 times 3x minus 5 dx. For a definite integral, we need to first of all take an antiderivative. But for antiderivative, there's no product rule. Here we need to FOIL first, and then use power rule to take an antiderivative. So let's FOIL first. If I FOIL 2x minus 1 times 3x minus 5, that's 6x squared minus 10x minus 3x plus 5. If I combine like terms, that's 6x squared minus 13x plus 5. So if I FOIL, I get 6x squared minus 13x plus 5 dx. Next, I have this power rule to take antiderivative, which is 6x to the power 3 over 3 minus 13x squared over 2. For a constant, we apply constant rule. That means take constant times variable. I get 5x. Evaluate from -2 to 6, which means I plug in 6 and then plug in -2 and take difference. If I plug in 6 for x, 6 to the power 3 is 216. 216 times 6 is 1296. 1296 divided by 3 is 432. If I plug 6 here, 6 squared is 36. 36 times 13 is 468. 468 divided by 2 is 234. If I plug 6 here, 5 times 6 is 30. Then plug in -2. -2 cube is -8. -8 times 6 is -48. -48 divided by 3 is -16. If I plug in -2 here, -2 squared is 4. 4 times 13 is 52. 52 divided by 2 is 26. 5 times -2 is -10. Then use calculator for the rest. Here I get 280. Next, integral from 1 to 4. 2x squared minus 1 over square root of x dx. For definite integral, we must take antiderivative first. But for antiderivative, there's no quotient rule. Let's simplify this expression first. This expression 2x squared minus 1 over square root of s, it can be rewritten as 2x squared minus 1 over x to a half. Square root of s can be rewritten as x raised to a half. Then it can be rewritten as 2x squared over x to a half minus 1 over x to a half. Then if I simplify, I can use upper exponent minus lower exponent. 2 minus half is 3 half. When I bring x to a half from bottom to the top, I change exponent from positive to negative. So that's the simplified expression for this. Next, take antiderivative for this expression. I get 2x raised to 3 over 2 minus x raised to negative 1 over 2. Use power rule here. Add 1 to the exponent. 3 half plus 1 is 5 half. And then divide by the new exponent. Same thing here. Apply power rule. Add 1 to the exponent. Negative half plus 1 is half. Then divide by the new exponent. Evaluate from 1 to 4. If we simplify, our expression divided by fraction is the same as multiplying this expression by the reciprocal. So for 5 over 2, reciprocal is 2 over 5. Same thing. The expression divided by fraction is the same as saying taking this expression multiplied by the reciprocal. So we get 2 over 1 times x raised to a half. Evaluate from 1 to 4. If I simplify, this expression can be rewritten as 4 over 5 x raised to 5 over 2 minus 2 times x raised to a half. Evaluate from 1 to 4. If I plug in 4 raised to 5 over 2, that's 32. If I plug in 4 here, 4 raised to a half is 2. I get 2 times 2. If I plug in 1 raised to any power is 1, so I get 4/5. If I plug in 1 here, 1 raised to any power is 1, so I get 2. Then use calculator for the rest. Here in my calculator, I get 114 over 5. That's the answer to this definite integral. I get 114 over 5. That's the answer to this definite integral. Next, integral from 0 to pi sine x dx. For definite integral, we take antiderivative first. Antiderivative of sine is negative cosine. Evaluate from 0 to pi. If I plug in pi, cosine pi is negative 1. If I plug in 0, cosine 0 is 1. Double negative is positive. I get 1 plus 1, which is 2. That's an answer to this integral. Next, integral from pi over 6 to pi over 3. Cosecant square of x dx. For definite integral, we need to take antiderivative first. Antiderivative of cosecant square of x, that's negative cotangent of x. Then evaluate from pi over 6 to pi over 3. If we plug in pi over 3, cotangent pi over 3 is 1 over radical 3. Cotangent pi over 6 is radical 3. Then simplify. Double negative is positive. We get 3 we get radical 3 plus radical 3 minus 1 over radical 3. Here we can try to rationalize the denominator. If I try to rationalize the denominator, I can multiply the top and the bottom by radical 3. That's radical 3 minus radical 3 over 3. Then put this over 1. Find common denominator, which is 3. So I can multiply top and bottom by 3. I get 3 radical 3 over 3 minus radical 3 over 3, which is 2 radical 3 over 3. That's an answer to this definite integral. Next example. Integral from pi over 6 to pi over 4. Cosecant x times cotangent x dx. So for definite integral, we first of all take antiderivative. Antiderivative of cosecant x times cotangent x is negative cosecant x. Now evaluate from pi over 6 to pi over 4. If I plug in upper limit, cosecant of pi over 4 is radical 2. If I plug in lower limit, cosecant of pi over 6 is 2. And then double negative is positive. So the final answer is 2 minus radical 2. We run the positive term first. Double negative is positive. The final answer is 2 minus radical 2. Next example. Integral from negative 2 to 2. 3 times absolute value of x plus 4 dx. How do we take integral with absolute value? So for absolute value, keep the rule in mind. If x is greater than 0, then absolute value of x equal to x. However, if x is less than 0, then absolute value of x equal to negative x. Now here, is x positive or negative? From negative 2 to 2, x sometimes positive, sometimes negative. From negative 2 to 2, x sometimes negative, sometimes positive. So this integral, it can be rewritten as integral from negative 2 to 0 plus integral from 0 to 2 here x sometimes positive, sometimes negative. We know that when x is between negative 2 and 0, x is negative. When x is between 0 and 2 is positive. So I split this integral into two integrals, from negative 2 to 0, and then from 0 to 2. In the first integral, when x is between negative 2 and 0, x is negative. If x is negative, absolute value of x equal to negative x. So we get negative 3x plus 4 dx. For the second integral, when it's between 0 and 2, x is positive. And when x is positive, absolute value of x equal to x. I get 3x plus 4 dx. Then we solve each integral individually. For the first integral, take antiderivative. I get negative 3x squared over 2 plus 4x. Evaluate from negative 2 to 0. For the second integral, I get 3x squared over 2 plus 4x. Evaluate from 0 to 2. In the first integral, if I plug in 0, I get 0. If I plug in negative 2 squared is 4. 4 times negative 3 is negative 12. Negative 12 divided by 2 is negative 6. If I plug in negative 2 here, negative 2 times 4 is negative 8. That's the first integral. For the second integral, I plug in 2 first. If I plug in 2, 2 squared is 4. 3 times 4 is 12. 12 divided by 2 is 6. If I plug in 2 here, 4 times 2 is 8. If I plug in 0, I get 0. So together, negative 6 plus negative 8 is negative 14. Negative 14 is positive 14. Here, 6 plus 8 is 14. 14 minus 0 is 14. So the final answer, 14 plus 14 is 28. So if an integral contains absolute value, we must think of two cases. If absolute value is greater than 0, if x is greater than 0, then absolute value of x equals to x. If x is less than 0, then absolute value of x is negative x. Next, integral from 0 to 4. Absolute value of 3x minus 2 dx. So if the integral contains absolute value, we need to consider if what's inside is greater than 0, then absolute value equal to the expression itself. If what's inside is less than 0, then absolute value is negative of the inside. Now, is this expression positive or negative? Is this expression 3x minus 2 positive or negative? So let's first of all set this expression equal to 0. Set what's inside equal to 0. Solve for x. Here x is 2/3. 2/3 is between 0 and 4. Now here we make number line test. If 2/3 is between 0 and 4, make number line test. Here we pick test point between 0 and 2/3. I can pick 1/3 as test number. Between 2/3 and 4, I can pick test number. Make it easy, I can pick 1. If I plug in the test number, 3 times 1/3 minus 2. 3 times 1/3 is 1. 1 minus 2 is negative. So when s is between 0 and 2/3, what's inside is negative. Now plug 1 inside. 3 times 1 is 3. 3 minus 2 is 1, which is positive. So when x is between 2/3 and 4, what's inside is positive. So I can split this into two integrals. First of all, from 0 to 2/3. First integral is from 0 to 2/3. Second integral is from 2/3 to 4. When s is between 0 and 2/3, what's inside is negative. If the expression inside is negative, we take absolute value equal to the negative of the expression. So if the inside is negative, for the absolute value, we take negative of the inside expression. When s is between 2/3 and 4, what's inside is positive. When s is between 2/3 and 4, what's inside is positive. If what's inside is positive, the absolute value of the expression stays the same. We can drop absolute value. What's inside stays the same. If what's inside is negative, we drop absolute value and negative sign. If what's inside is negative, we drop absolute value and negative sign. If what's inside is positive, we drop absolute value. Everything stays the same. Then I can distribute negative sign here. I get negative 3x plus 2. Next, I can take antiderivative. For the first integral, if I take antiderivative, I get negative 3x squared over 2 plus 2x. Evaluate from 0 to 2/3. For the second integral, take antiderivative. I get 3x squared over 2 minus 2 minus 2x. evaluate from 2/3 to 4. Then we solve each integral individually. For the first integral, plug in 2/3. 2/3 squared is 4/9. 4/9 times -3 is -4 over 3. -4 over 3 divided by 2 is -2 over 3. If I plug in 2/3 here, 2 times 2/3 is 4/3. If I plug in 0, I get 0. That's in the first integral. For the second integral, if I plug in 4, 4 squared is 16. 16 divided by 2 is 8. 8 times 3 is 24. If I plug in 4 here, 2 times 4 is 8. Then I plug in 2/3. 2/3 squared is 4/9. 4/9 times 3 is 4/3. 4/3 divided by 2 is 2/3. If I plug in 2/3 here, 2 times 2/3 is 4/3. Then simplify. -2/3 plus 4/3 is 2/3. 2/3 minus 0 is 2/3. For the second parenthesis, 24 minus 8 is 16. 2/3 minus -4/3 is -2/3. -2/3 is +2/3. Then add them up. I first of all put 16 and 16 over 1. Then find common denominator. Yeah, common denominator is 3. So I can multiply top and bottom by 3. I get 48 over 3 plus 2 over 3, which is 52 over 3. That's an answer to this definite integral. Next example. Integral from 0 to 6. 2x squared plus x plus absolute value of 2x minus 1 dx. If the integral contains absolute value, we must consider two cases. If the inside is positive, we drop absolute value, everything stays the same. If the inside is negative, we drop absolute value and negative sign. Now, is this expression 2x minus 1 positive or negative? So let's first of all set 2x minus 1 equal to 0. If we solve the equation, s equal to a half. Half is between 0 and 6, so let's make a number line. From 0 to 6, half somewhere between 0 and 6. Let's use number line test. Pick test number between 0 and a half. Here I can pick a quarter. Next, pick test number between half and 6. It could be any number in the middle. To make it easier, let me pick number 1. 1 is between half and 6. Now, plug test number into an absolute value. If I plug in a quarter here, 2 times a quarter is a half. Half minus 1 is negative, which means when s is between 0 and a half, what's inside the absolute value is negative. If I plug in 1, if I plug 1 into an absolute value here, 2 times 1 is 2. 2 minus 1 is 1, it's positive 1, which means when s is between half and 6, what's inside absolute value is positive. So here I can split its absolute value into two pieces. Split the integral into two pieces. From 0 to a half. 2s squared plus x plus absolute value of 2s minus 1 dx. Plus integral from half to 6. Integral from half to 6. 2s squared plus x plus absolute value of 2s minus 1 dx. Then we solve each integral individually. For the first integral, when s is between half and 0, 0 and half, what's inside? What's inside absolute value is negative. If what's inside is negative, we drop absolute value, add negative sign in the front. If what's inside absolute value is negative, we drop absolute value, add negative sign in the front. When s is between half and 6, what's inside absolute value is positive. If what's inside absolute value is positive, we drop absolute value. Everything stays the same. If what's inside absolute value is positive, we drop absolute value. Everything stays the same. If what's inside absolute value is negative, we drop absolute value, add negative sign in the front. Then solve each integral individually. For the first integral, I can combine like term first. X minus 2x is negative x. Minus negative 1 is positive 1. In the second integral, I get 2x squared. X plus 2x is 3x. Minus 1 dx. Then take antiderivative. I get 2x to the power of 3 over 3 minus x squared over 2 plus x. Take antiderivative. Evaluate from 0 to a half. For the second integral, take antiderivative. We get 2x to the power of 3 over 3 minus plus 3x squared over 2 minus x. Evaluate from half to 6. Then we plug in the upper and lower limit and take the difference. If I plug in half here, half cube is 1a. 2 times 1 over a is 1 over 4. 1 over 4 divided by 3 is 1 over 12. Half square is 1 over 4. 1 over 4 divided by 2 is 1 over a. Plus half. If I plug in 0, I get 0. That's the first integral. For the second integral, plug in 6 first. 6 to the power 3 is 216. 216 divided by 3 is 72. 72 times 2 is 144. If I plug in 6 here, 6 squared is 36. 36 divided by 2 is 18. 18 times 3 is 54. Minus 6. If I plug in half, half cube is 1 over a. 1 over a times 2 is 1 over 4. 1 over 4 divided by 3 is 1 over 12. Half square is 1 over 4. 3 times 1 over 4 is 3 over 4. 3 over 4 divided by 2 is 3 over a. If I plug in half here, I get half. Then simplify. Here I use my calculator here. I get 11 over 24 in the first integral. I get 11 over 24. For the second integral here, I use my calculator. I get 4,609 over 24. Together, I get 4,620 over 24. Then I divide top and bottom by 12. I get 385 over 2. That's an answer to this definite integral. Next example. Integral from negative 2 to 2. Square root of 4 minus x squared dx. If we try to solve this definite integral normally, we need to take antiderivative for this expression here. But so far, we don't have any technique to take antiderivative for this expression. So in this case, we think of area under the curve. If we cannot find antiderivative for this expression here, we should think of area under the curve. So what's the area? How this graph looks like? This function is y equal to square root of 4 minus x squared. If I square both sides, I have y squared equal to 4 minus x squared. And if I add x squared to both sides, I get x squared plus y squared equal to 4. That's a circle. That's a circle, center and origin with radius 2. That's a circle, center and origin with radius 2. Since y is positive, we only have an upper half semicircle. Since y is positive, we only have an upper half semicircle. So it's an upper half semicircle, center and origin of radius 2. From negative 2 to 2, the area under the curve from negative 2 to 2 is a semicircle. The area under the curve from negative 2 to 2 is a semicircle. So for this integral, we solve it using area. Area of a circle is pi r squared. Since this is a semicircle, so it's half of pi r squared. For this circle, radius is 2. Simplify, I get 2 pi. So for any definite integral, if we can find the antiderivative, we should consider the area under the curve. Next example. Integral from 0 to 3, 4 plus square root of 9 minus s squared dx. Again, for definite integral, we need to take antiderivative for each term here. Antiderivative of 4 is easier, but for antiderivative of square root of 9 minus s squared, so far we don't have any technique to take antiderivative for square root of 9 minus s squared. So think of area under the curve. First of all, this integral can be rewritten as integral from 0 to 3 of 4 dx plus integral from 0 to 3 square root of 9 minus s squared dx. Let's solve each integral individually. For the first integral, I can take antiderivative. I get 4x, evaluate from 0 to 3. If I plug in 3, I get 12. If I plug in 0, I get 0, which is 12. So the answer for the first integral is 12. For the second integral, it cannot be solved normally, so we need to think of area under the curve. Here the function inside is y equal to square root of 9 minus s squared. If I square both sides, I get y squared equal to 9 minus s squared. If I add s squared to both sides, I get s squared plus y squared equal to 9. That's a circle, center and origin with radius 3. That's a circle, center and origin with radius 3. Since y is always positive here, we only have an upper half semicircle. So we don't have a lower half. We only have an upper half semicircle since y is always positive here. Here y is square root of 9 minus s squared. Square root is always positive. So we only have an upper half semicircle. We're taking integral from 0 to 3. That means we're looking for area under the curve from 0 to 3. Area under the curve from 0 to 3 is a quarter of a circle. We know that area of a circle is pi r squared. Since this is a quarter of a circle, we take a quarter times pi r squared. Here r is 3, radius is 3. If I simplify, I get 9 over 4 pi. So for the final answer, adding up, I get 12 plus 9 over 4 pi. 12 is the answer to the first integral. 9 over 4 pi is the answer to the second integral. So for the answer of this integral, we add the answer together. It's 12 plus 9 over 4 pi. Next example, integral from negative 4 to 0. 2s squared minus square root of 16 minus s squared dx. When we try to solve a definite integral, we need to take antiderivative for the function inside first. Antiderivative of 2s squared is easy, we can use power rule. How about antiderivative of square root of 16 minus s squared? So far, we don't have any technique to take this antiderivative. So think of area under the curve. If we can find antiderivative, think of area under the curve. This integral can be written as integral from negative 4 to 0, 2s squared dx, minus integral from negative 4 to 0, square root of 16 minus s squared dx. I first of all split this integral into two integrals. Solve each one individually. If I solve the first integral, I have 2s cubed over 3 using power rule. Evaluate from -4 to 0. If I plug in 0, I get 0. If I plug in -4 cubed is -64. -64 times 2 is -128. So I get -128 over 3. Double negative is positive, so I get 128 over 3. That's an answer to the first integral. That's the answer to the first integral. Now for the second integral, what do we get here? The function inside the integral is y equal to square root of 16 minus s squared. If I square both sides, I get y squared equal to 16 minus s squared. Then I can add s squared to both sides. If I add s squared to both sides, I get s squared plus y squared equal to 16. That's a circle center and origin with radius 4. And since y is positive, we only have an upper half semicircle. So it's a circle center and origin with radius 4. And it's an upper half semicircle. For integral, we're looking for area under the curve from -4 to 0. For this integral, we're looking for area under the curve from -4 to 0. So that's what we are looking for here. Area under the curve from -4 to 0. This is a quarter of a circle. Area of a circle is pi r squared. So take a quarter times pi r squared. For this circle, radius is 4. If we multiply 4 squared is 16. 16 times 1 over 4 is 4. I get 4 pi. So the area under the curve is 4 pi, which means this definite integral is 4 pi. Then for the final answer, we take the first integral minus the second integral. I get 128 over 3 minus 4 pi. That's the answer to this definite integral. Next example. Integral from 0 to 5 s cubed plus square root of 25 minus s squared dx. So for definite integral, we take antiderivative first. For antiderivative of s cubed, that's easy, we can use power rule. And for antiderivative of square root of 25 minus s squared, so far we don't have any technique. If we are not able to take antiderivative for some expression, try to think of area under the curve. So I can first of all separate this into two integrals. First integral from 0 to 5, s cubed dx. Second integral from 0 to 5, square root of 25 minus s squared dx. Let's solve each integral individually. If I solve the first integral, I use power rule here. I get x to the power 4 over 4. Evaluate from 0 to 5. If I plug in 5 for x, 5 to the power 4 is 625. 5 to the power 4 is 625. So I get 625 over 4. If I plug in 0 for x, I get 0, which is 625 over 4. That's an answer to the first integral. For the second integral, since we are not able to find antiderivative for this expression, think of area under the curve. Y equal to square root of 25 minus s squared. If I square both sides, I get y squared equal to 25 minus s squared. If I add s squared to both sides, I get s squared plus y squared equal to 25. That's a circle center and origin with radius 5. That's a circle center and origin with radius 5. And since y is always positive, This is the upper half semicircle. For this integral, we're looking for area under the curve from 0 to 5. We're looking for area under the curve from 0 to 5. That's a quarter of a circle. We know that area of a circle is pi r squared. This is a quarter of a circle, so it's quarter times pi r squared. 25 squared is 25. 25 times 1 over 4 is 25 over 4 pi. So for the final answer, we add these two integrals together. We get 625 over 4 plus 25 over 4 pi. That's an answer to this definite integral.